Is entitled Learn the Ways of the Force Is. It says, I want to learn the ways of the Force, Luke Skywalker. So, what we want to do is we want to look at the various types of forces that we have here. There's actually more than one. So, our learning goals include we want to be able to draw the magnitude and direction of all forces acting on an object. For most of the times, there's going to be more than one. We want to describe the motion of an object based on a free body diagram. So there are set rules for drawing these forces. And we want to be able to relate these free body diagrams that we draw to the concept of net force that we learned about in the second law of motion. So multiple forces. First things first, you have multiple forces. It says most objects experience more than one force. And if you have a situation like this, like we had in the lab, you can look at it and you can say, okay, this box right here is experiencing a force. Gravity is trying to pull it down. Now it doesn't actually move down, so there must be another force that's counteracting this gravitational force. But in addition to that, you also have a force that's pulling it to the right. And that is this block right here. By it's hanging right here, and the pulley is pulling it to the side. So most objects experience more than one force. And it turns out that you can combine these forces by something called vector addition. So in other words, if I have a force of 10 newtons to the right and another force of 20 newtons to the right, those two together can be treated as one 30 newton force to the right. So you can add these forces together if they're in the same direction. Now if you push it 10 to the right and 20 to the left, what you're going to end up with is you're going to end up with a force of 10 newtons to the left. So you have to be able to combine these things using the rules that we talked about with vectors. So forces are vectors and therefore must include magnitude and direction. It's not enough to say a force of 5 newtons. You've got to say it's a force of 5 newtons north, south, east, west, up, down, some sort of direction along with that. So now we take a look at multiple forces. It says we draw the forces out from the center. So we take an object and we generally represent an object as a dot because we don't want to spend a whole lot of time drawing a person or a plane or a car. You can draw an awesome car. Okay, we don't want to spend our time doing that. And so instead we represent the object with a dot. And now what we do is we draw all the forces that are acting on this object drawn out from the center. So this arrow is coming out from here, this arrow is coming out from there, and so on. We have two really important key terms right here. So you have equilibrium. Equilibrium results in constant velocity or no motion. That is when forces cancel out. So in other words, the left force and the right force cancel out, and the up force and the down force cancel out, leaving no net force on it. So that right there is what we call equilibrium. Whenever you have equilibrium, it results in a constant velocity or no motion. Now, how do you decide what it is? It depends on the stem of the question. So the stem of the question, in other words, the information that's given to you in a question, can say an object is moving at 10 meters per second and then experiences these forces. Well, these forces right here indicate that there is no change in motion. But since it was moving to begin with, it would be constant velocity. You have to pay really close attention to what is said in the question. The second term is net force. Now we talked a little bit about net force when we talked about Newton's second law. We said F net equals ma. But we kind of skipped over this F net and said we'll come back to that later. F net is a combination of all the forces that we have using vector addition. So in other words, you have a net force when maybe this force right here is 5 to the right and this force right here is 4 to the left. Well, the net force, since these are going in opposite directions, would be 1 Newton. So we have a variety of forces that we can look at whenever we're looking at forces. The first one that is almost always present, and it is always present as long as we're on Earth, is the gravitational force. That's what pulls you down to the ground. Okay, that is the mutual attraction between any two objects with mass, and since the Earth itself is much, much more massive than anything close by, it is the gravitational pull that pulls you down. For any object on Earth or any object that is close to Earth, there is going to be a gravitational force. Now, just because an object is in space does not mean that it will not have a gravitational force. For example, you could have a spaceship on the moon and there is still gravity on the moon. Okay, for some reason people think there's not. There's still gravity on the moon. There's gravity caused by the sun. Okay, there's always going to be a gravitational force unless it says otherwise. Now the applied force is the push or pull that you exert on something. So in this case, it would be the guy who's pushing the lawnmower. So it's a directly applied force, and we signify it as Fa. The normal force is the force that is exerted by the surface on an object. So for example, we know the gravitational force is pulling this lawnmower down. But the reason why the lawnmower does not go down through the ground is because there's a ground right here that stops it. The ground itself exerts a force on the object upwards that we call the normal force. So it is the force that is exerted by the surface on an object. It usually counteracts the gravitational force, but we'll get into that more a little bit later. You have the frictional force. The frictional force is the force that force resisting motion. So if an object is moving down and to the left, friction is moving up and to the right. If an apple is falling down, friction is counteracting it going up. Anytime you have motion, you have friction that is resisting that motion. And that's signified by FF. Now, you are not limited to these four things. There are other letters that can indicate other types of force. Later, we're going to talk about the electrostatic force. We may talk about the spring force. Okay, you may talk about the tension force in your class. But all of these are forces first, and then you signify what type of force it is with a little bit of letter. So all of these are measured in the unit of the Newton. All right, a free body diagram. A free body diagram for a ball at rest. All the forces are labeled. So the first thing, you can't just have arrows going every which way. Okay, you have to draw these arrows, and you have to draw them proportional to the force. So if you look right here, I have a ball at rest. I indicate it with a dot. And then what I do is I draw the two forces going down and up, because the ball is still attracted to the floor by gravity. But the ball can't go through the floor because there's a normal force upwards. So these two forces actually cancel each other out. So if you look, I drew these two forces the same length. Now, it's not enough just to have these forces here. You have to label them. You have to say, this is the force due to gravity and this is the normal force. A lot of times when you're drawing these, it's helpful to go ahead and say Fn equals Fg. That indicates, hey, this is what I know I'm talking about. I may not have drawn the arrows perfect, but this is what I was trying to do. Now, free body diagrams can be used to calculate the net force. In this particular case, the net force is 0 because both of these forces are equal. They cancel each other out. But free body diagrams are a good thing to be able to find the net force from. So we have an example. It says, describe the motion of the object based on the free body diagram. So you look at the free body diagram, and you could get a ruler out, or you can just kind of eyeball it. But it looks to me like the applied force is equal to the frictional force. So those two are going to cancel each other out. And it looks to me like the normal force is equal to the gravitational force. So what I can say is I can say Fn equals Fg. Since one is up and one is down, they cancel each other out and there's nothing left. I can say that Fa equals Ff. And they cancel each other out because one is left and one is right. So what I can say is that the net force acting on the object is 0. If the net force acting on the object is 0, you can say one of two things. You can say the object is moving at a constant velocity, or you can say it is at rest. And so we have to decide which one based on the stem of the question. So we look back and we say, is there any sort of indication it was moving to begin with or at rest to begin with? And in this case, there's not, so both of these are acceptable answers. This says, draw the forces acting on a rocket accelerating upward toward the International Space Station. You should be able to use your descriptions and your knowledge of free body diagrams to go ahead and put together a free body diagram that looks like this. And you should be able to reproduce this same thought process on any sort of quiz or test. This is draw a free body diagram for a drop of water in free fall. There are not always multiple forces. In fact, you have situations in which there's one. You should be able to justify why there is just one force when you're looking at this term right here. This is a term from Unit 2, and so you should be able to go back and say, what does that term mean in terms of forces? So let's take a look at Newton's second law again. Now remember, we said that F net is equal to mass times acceleration. Well, remember, this F net, okay, not more on this later, we're talking about it now, is the sum of all the forces. Now, we use this term sum of the forces not to mean that you add all the forces together, but you combine them using vector addition the way they're supposed to. So it could involve finding the sum of the forces, subtracting them. If you're in an upper level class, you may end up using trigonometry to resolve forces. But what you're trying to do is you're trying to describe the total forces that are acting on an object. Acceleration and mass are nothing new. So let's go ahead and take a look at what this looks like whenever we use them together. So it says determine the acceleration of the truck based on the free body diagram below. So I know I'm using forces, and I know that the only expression that I have between force and acceleration is F equals ma. More specifically, F net. So you can use the free body diagram and you can say, okay, what is my net force here? So let's always start with the up and down force. I have 80 newtons up, I have 80 newtons down. Those cancel each other out and they are gone. I have 100 newtons left, I have 80 newtons right. Those don't cancel each other all the way out. Instead, what I'm left with is 80 newtons to the left. So my net force would be 80 newtons to the left equals, now here's a problem, I don't have the mass, or so you may think. If you look at the free body diagram, you're given the weight of an object. Remember, the weight of an object is always equal to the mass times the gravity. So whenever you're given the weight of an object, you're also given the mass, because you just plug in, you would say 80 equals 9.8 m, divide both sides by 9.8, and when you do that, you would get the mass of the object. I'm just going to kind of leave it right here as 80 divided by 9.8, and what I'm going to do is I'm going to go ahead and plug it into the equation. So this is now my mass right here, 80 divided by 9.8. And you probably see why I did that right away, because you have 80 equals 80 divided by 9.8 times A. So you should realize right away, without using a calculator, that you can actually plug in A equals 9.8, and that would solve this particular problem. Okay, if you're more comfortable solving for the mass first and then plugging it in, feel free to do that. Now, the one last thing is, remember, acceleration is a vector quantity. So it's not enough to put 9.8 meters per second squared. You have to indicate the direction. And in this case, the direction is going to be left. Acceleration is always in the same direction as the force. Example B2, it says a 10 kilogram object is accelerated on a frictionless surface at 2 meters per second squared. Draw a free body diagram for the box. You should be able to draw a free body diagram in which you label the forces and tell me what they are, and you should be able to justify why this is the free body diagram. Now, I will give you a hint. You do have to take a look at the forces and F equals ma to solve for these this particular free body diagram. So these are the three forces. Now, some people say, what about friction? Well, it says it's a frictionless surface. It says a person is pushing a car to the gas station, capable of pushing 100 newtons of force, but only manages to maintain constant velocity. Use a free body diagram to explain what is occurring. So we still have our car. That car is going to have weight, and it's going to have a normal force, and those two are going to cancel each other out. If he's exerting 100 Newton force to the left, you should be able to justify why the frictional force is 100 newtons to the right. And you should be able to figure that out based on what we've talked about in this lecture.